and welcome to my gentle introduction into machine learning. This is one of the talks you can forget afterwards if you want. Nobody's going to hit you if you didn't really follow closely. It's also not really meant to follow really closely, but it's just meant as a gentle introduction. It might be fast at times, but just don't worry. Sit down, relax, maybe a slide or two later, you're on it as well. So the reason for giving this talk is fundamentally like playing around with stuff and my passion about pattern recognition, natural language processing, machine learning stuff. Before being software developer and project manager and whatnot, I was spending 10 years at universities doing handwritten digit recognition, handwritten just whatever recognition, and natural language processing later. But that was 10 years ago. I needed a job for money. At that time, machine learning was really obscure, and just a bunch of weird guys did do this. And as it's going into hype cycle right now, I thought it might be a nice time to catch up with the most recent developments and share some of the interesting stories with you. So you might have heard about losing against the system AlphaGo that was built by DeepMind. By talking to colleagues, one of the frequent questions is, what is actually the difference to playing against machines, well, most likely losing against machines 20 years ago when they lost against the chess system of IBM. And instead of trying to explain myself, I'd like to show a short video clip that explains the difference first from a machine learning or from a machine perspective, what the difference is between playing chess and playing the Go game.
The ancient Chinese game, Go, has as many more possible moves than chess as there are atoms in the entire universe. So there's no way of just moving the board. That's practically impossible. For this reason, Go is the holy grail of AI, and learning to do such a task from scratch is a huge feat.
Well, this is basically what they have done at, kind of my setup is messed around. What they did at DeepMind. And this is showing the difference from the system perspective of playing Go versus playing chess. And from a more human perspective, I'd like to show a clip of Demis Hassabis, one of the co-founders of the DeepMind company, and I hope I find it pretty quickly. Sorry if I have to relook at this one again. But
to do such a task from scratch is a huge feat.
So the next clip should
why they play a particular move. Sometimes they'll just tell you it felt right. So one way to think of it is that Go is a much more intuitive game, whereas chess is a much more logic-based game.
So an intuitive game playing by systems, this is kind of a challenge in itself. So the question is, how do we build and train a system that this should be more based on intuition than really making hard calculations? And again, the Demis Hassabis guys from DeepMind is going to explain how they did train their system. And I have, okay.
DeepMind claims that their system is not pre-programmed and it learns from experience using only raw pixels as data input.
So the way we start off training AlphaGo is by showing it 100,000 games that strong amateurs have played that we've downloaded from the internet. And we first initially get AlphaGo to mimic the human player. But of course, ultimately, we would like AlphaGo to be stronger than human amateurs and compete with the top professionals. So the way we do that is, after we take that first version that's learned to mimic human play, we then allow it to play itself 30 million times on our servers, and using reinforcement learning, the system learns to improve itself incrementally through avoiding its errors and increasing and improving its win rate against older versions of itself.
So he was mentioning the reinforcement learning, and before we go into more the algorithmic part of this one, I'd like also to mention there is a hardware part. There's also a hardware part similar to the hardware part of the IBM guys winning the chess games. And what they did use, they did TPUs, because GPUs, well, it's so yesterday, no? So the TPU is a tensor processing unit. It's custom-built piece of hardware ASIC to boost machine learning. So it was custom-built to boost TensorFlow computations, really low precision math, but massively parallel matrix computations. What they did get out of it was something like they estimated 3 generations of Moore's law. So they could have today the processing power you usually would expect in 6 years. So they did take into account that they should also have lots of processing powers to do something like that. But the other side, this we've heard before, this is the reinforcement learning. Actually, it's called deep reinforcement learning. Let's go back to 2014, and the same DeepMind company, they had one of their earlier Nature publications using something like a system that plays Atari games. And this is just a breakout game, and again here, what made it into the Nature publication was this deep reinforcement learning. And just using, instead of just using this expression, I'd like to briefly introduce what it is. Again, you don't really have to understand, but I hope that you get the gist of this one. Let's start with Markov decision process. This is a formal description of something where you have an environment, in that case the Atari breakout game, where you have an agent that performs action. You have the actions such as the bar moving left or right, or releasing the balls when you have lost the ball in the breakout. It has a state, well, where the bricks are and stuff like that, direction and the velocity of the ball. And from time to time, there are rewards. Rewards, the thing gets if the ball is going to hit one of the bricks. Graphically, above we have the environment, and the agent below, he can perform actions, and the environment is responding back by state changes, and from time to time, there is a reward. That's basically the Markov decision process. Nothing with reinforcement learning, it's just this simple thing. The reinforcement learning, or Q learning, is basically taking this process we have seen before, and it adds one thing, the quality function. This is an estimate of the maximum. Continue to play when data first. The challenges with the data is it's really hard sometimes to get access to the right data. Sometimes it's even harder to get enough or lots of data, and it's kind of an unwritten law, there's never enough data. The real world lessons is it's really a crucial part for successful machine learning projects, and I can tell you this is really not the exciting part of machine learning. Getting data, formatting data, bringing it into the proper format to do stuff, this is really boring, takes a lot of time, and sometimes you feel really bad doing this. Anyway, it always takes much longer than anticipated. Just some examples. This is just text. Each line is an example. If you make this larger, we have sentiment stuff. So we have kind of an ID here, an outcome, like this is a negative review, and the text that belongs to it is just a bunch of words, and each line is representing such a sample. Another example is the MNIST database. This was collected from census and students, handwritten digits, something like 70 or 80,000 examples. The task here is you get an image, you need to find out what digit it is. Another one, this is just a bunch of a high-dimensional vector space. This is breast cancer data. You have, again, an ID, and the B size benign, a nice one, and the malignous, this is the bad cancer part, and then you have a number of 30 measurements on that kind of data. And finally, from an ImageNet competition, the task there was you get 1 million images, train stuff, and you need to, given an image, tell me what it is that you see in the image. In that case, one example is you get an image of a flower, and the system is supposed to figure out that this is a rosemary. So this gives you a rough idea about the diversity of the data. Of course, there's much more, but you have to stop somewhere. So next topic, models. This is really an old model, neural network. Also a really old model, decision tree stuff. This is Gaussian mixture models, is kind of newer. And these were hidden Markov models. This is what I did at university at those times. This was really state of the art for acoustics and speech recognition, handwriting recognition. Even more modern were conditional random fields and more modern subpaired vector machines. And then something happened around these times. Nobody would listen to anybody just using the term neural network. Everybody knew that they don't really perform or they're too hard to train. But in 2012, some group from Canada with Jeffrey Hinton, they participated in this ImageNet contest, and their system was so much better than everything else that this is really kicking off the whole deep learning stuff. And deep learning means basically it's a neural net. And you have an input layer. Here is the image, 224 times 224 pixels, thickness of 3 because you have colors. So for each pixel you have 3 colors, and the output, here's a vector of 1,000 that gives you per class the probability that this picture here belongs to that class. And there in between, there are layers and layers and layers and layers. And they figured out how to train something like that in a reasonable amount of time with some good quality. And from 2012, the whole deep learning stuff really took off. And it was called deep learning basically for marketing reasons. They couldn't say neural networks anymore, but they thought like deep learning sounds cool, and it really was for them. So categorization of machine learning. If you really want to get more into this, there are excellent online resources. Everything is openly available. You don't have to pay anything. This is the outline of the class at Stanford Machine Learning from Andrew Ng. Initially, you get some supervised learning. Basically, this is learning from examples. And for each example, you know the right answer. Another class of machine learning stuff is unsupervised learning. What do you do there? You get lots of data, and the task is not to figure out what it is, but to discover structure. You can use that, for example, for dimensionality reduction, outlier detection, stuff like that. And one of the last chapters, and also important, we have seen reinforcement learning. It's basically interacting with a dynamic environment. This is really important also for robotics and stuff. And as we have seen, there's also a reward function. So much for this introduction here. Now we do some demo time. I have 3 demos, out of which, of time reasons, I do only 2. I would have had outlier detection first, basically breast cancer data, this high-dimensional data space, figuring out which ones are outlier or maybe correspond to the malignous cases. Then sentiment analysis for movie reviews and pattern recognition on the MNIST database. The first one, I just showed the slides. We have seen the data here. And there is some kind of baseline algorithm which is called local outlier factor. It's pretty simple, so you can find direct implementations in a few Java classes. I've already done that, but it's kind of simple from the concept. It goes like this: you have 2 clusters. one dense cluster on the bottom left and one more open cluster on the upper right. And the idea is to find outlier. What I did is define a distance metric that says, how alone do I feel as a point compared to my neighbors? And the trick is, if you're in the lower corner, having the distance between these 2.56 points to this cluster, let's say this guy, he feels really alone compared to his neighbors. Whereas if you're somewhere here, they're not closer to their neighbors, but they don't feel as alone. And using this distance metric, you can then threshold off. Basically, you say whatever is 1 or less, I assume this is contains to some cluster, and if it's larger, then I'm more likely to be an outlier. And depending on the threshold, you can then decide how many cases you want to have. If you really want to find all, or if you want more the case, if you find something, then you want to be sure that it is. It's basically the local precision trade-off that you can do here. So let's move to the next example, the sentiment analysis. Movie review data we have already seen. For this is one of the most simple models, the naive Bayes model for classification. And this is not programmed, but it's just using the Mallet toolkit. Mallet toolkit is a toolkit for statistical natural language processing. It's quite old and robust, and it's one of the older frameworks or toolkits to do this. It's open source, it's also Java-based, and here I would have to switch over. So what we see here is basically the demos inside of a GitHub repo, and on top of it I have one demo for deep learning for J, I have one for Mallet I'm going to show now, and I left out the outlier. Everything is in a Docker container itself, so this forced me to have a reproducible setup, so it should be easier to play around afterwards. And in each section, you also have kind of the relevant publications to it, and the data and whatever is needed. So let's start with the Mallet kind of guy. I should have, no, this is the next one. Yeah, here. So I look into the data. I see this polarity data, I have test data, train data, and the next thing I'm going to do, let's look at the data to verify that this is actually what we want to use. And then as this is a toolkit, we cannot just do something, but we first have to import this text data into some format that is fine for this toolkit. Oops. My Docker container feels alone. So I'm sorry, I will continue on the slide, and I hope that the next Docker container is not letting me down again. In this case, this is handwritten digits with the MNIST database, and this is the first one with a deep neural network, the LearnNet 5. And for this, the framework to use, I did use deep learning for J, which is much more recent, and it's open source Apache, and of course it's also Java. Here, the model is convolutional neural networks. You put some digit here, you have convolutional layers, at the end you have a normal classifier setup of something like that. And this is not so recent. Actually, the LeCun guy, he did this paper in '98, which is long before this deep neural network took off. So it's kind of a deep neural network, but it's the hello world for deep neural networks if you want. And then it took really a long time until people realized what Jan LeCun did with this publication. And if I look at the Java code, this network above, this is the description in the Java code, how to set up all the layers to get what you have seen here. Of course, it took them at that time much more programming and much a longer time. If it would have been as simple, people would have much faster realized how useful this is, what they did. And let's check it here. Go back. So here I have, or should have, again, the data. These are the MNIST data as downloaded from the internet. I have test stuff. This is like 10,000 images for testing and around, I think, 60, 80,000 for training. And here I don't have only the data, but I also have the trained deep neural networks. The reason for this is on this laptop training takes a whole night, so it's kind of difficult to demonstrate. This is why I wrote the model to disk. And the first thing I'd like to show is using these models and running through all the 10,000 test images. So it's first going to load the model from this model file. Then it should load the images from the disk. and then evaluate the model on the 10,000 images. So it's running through each image, and it's comparing the output with the known result, basically what kind of digit it should be. At the end, we get some performance results, like a precision stuff like that, and here's the confusion matrix. So basically it says it has something with a label 9, it has been classified as a 9 999 times, and these are the cases where something went wrong. We can have this as the result, basically, like training this for one night or even less on a normal laptop, you get something that performs better than what people have been trying to do for decades with whatever mechanisms they were using. So let's go back to the slides. Everything is on GitHub. I'm not finished with documentation, and there are some glitches here and there. I try to improve over time, but I would not really like to promise hard, but I really try to make this something like a quick start. Now, come to recent advances. Towards the end of the talk, one of my defays from Facebook guys, automatic image captioning, TensorFlow library, and the differential neural computer, something really new, the latest DeepMind publication like 1 month ago. Deepface, in 2014, the Facebook guys, they did a deep neural network, and they really came close, or probably they're really at human level performance in recognizing faces today. So this is state of the art. If you put in whatever image of a face, you can be pretty sure that what the machine does is at least as good what you can do. Also 2014 in Stanford, there's image captioning. Basically, it's not only finding what the image is, but it's finding a description for the image. And for all those who like to take lots of pictures, but they don't like to have a nice way to archive those, this is going to save you. Feel happy, take your pictures, there will something come along, it will describe the picture view, you can put your question in natural language, and it will give back the pictures to you. And you can expect this in like a couple of years. Or at least, if we cannot have this in 2 years, I'm kind of disappointed. Anyway, so on the left-hand side, I don't know if you can read it. It says construction worker in orange safety vest is working on the road. Then 2 young girls are playing with Lego toy, and boy is doing backflip on a wakeboard. Well, I don't really know about the wakeboard. There's kind of sand in front of it, but it obviously have seen people doing jumps like that and has read description that this could be a backflip, and there was some water, so it's okay to think it's a wakeboard. Then 2015, here I took this example to demonstrate how open the machine learning community usually is. So whatever these guys are doing, they're publishing the stuff in open archives and open journals. The data is in many cases open, and all the machinery or the mechanisms are also available as open source libraries. So it's really, really cool to follow in. And well, there's one exception, I guess. Apple guys, they're using tons of machine learning as well, but they don't publish anything. They don't have open source software. They don't have open data. So it's this is kind of the exception to the rule. And this is the differential neural computer. The drawback of the deep learning so far is that they're really good in many cases, but they don't have a memory. So they're really good locally, but if they do something, they forget what they have done before. And the idea is what was here to work around these shortcomings, because they really wanted to attach some memory to this possibility of deep neural networks. And the question is how you do that. We know from what we do in our daily jobs that standard computing is really good with data structures and algorithms, and all that works perfectly, also at really, really high speed, but you have to tell the system what to do. And their idea was that the system should figure out on its own. And the way to do this was basically attaching some form of memory that can be managed by the neural network via associative memories, and not really telling how it's done, but the way it accesses the memory for writes, deletes, and updates is done in a way that you can calculate differentiations to it, and then you can use the complete learning algorithm. So you just store tons and tons of graph and question, and over time, it learns how to organize itself from new information. So if you put the London Underground map into it and you ask how you can go from A to B, it's actually capable to tell you how to do that. But nobody told the system how to organize graphs or how to do shortest path problem on something. I think it's really pretty amazing. So let's say we aim to combine the advantages of neural and computational processing. The computational processing is the classical part, by providing a neural network with read-write access to external memory. And this is the crucial part. The whole system is differentiable and can therefore be trained end-to-end with gradient descent. So this makes the system, it allows the system to learn how to organize its own memory. And of course, the London Underground and getting a Nature publication with London Underground shortest path problem, it sounds kind of weird, but if you have seen what they did with the Atari Breakout game, then maybe there is much more in the future. If some other guy would come up with something like that, I thought, yeah, sure. But if these guys say something like that, it might be really worth paying attention. Food for thought. Will we lose our jobs? Well, I don't know. This is kind of job curves over the decades. What you have seen here in 1990s, these were the times when industry really pushed lots of computers, and this was kind of hard for the routine stuff. So routine cognitive, routine manual work just went flat after that, didn't grow anymore. And the next hit to the routine, especially the hard hit, was here, financial crisis. The cognitive non-routine work did also kind of a hit, but not that bad. And it really is the question, what's going to happen now, here, or in the near future? And it's really, well, better not to make too many guesses, but, well, there's a positive side. And especially from statement by Lisa Dahl, the guy who lost against AlphaGo. I think this is pretty impressive, what the guy is saying after losing something like that. So he really is hinting that it might be that these systems are not taking all our jobs away. These systems might help us to do our jobs better. So this is also a possibility. And we should not always look at the black side, but maybe sometimes things are also getting better. So take-home messages, what have we seen? Deep learning really was a breakthrough from machine learning, and it reaches now human-level performance on many tasks. The future, well, yeah, some jobs will get obsolete. I'm pretty sure of that. And also, I think there might be new jobs that emerge, or changed jobs compared to today. Whatever there will be, the transition will be challenging. It's kind of industrialization in a different way. So when the new machines come, or the people do manual work in these big offices, or not offices at that time, but how do you say? Shit. Anyway, you know what I mean. There was a big transition as well, and this might be another transition. I don't know if it's as big as the last one, but I think it might be one. So in the meantime, get your hands dirty. And tools are simple enough to be used outside of labs. And the example on GitHub that showed you, maybe one or two of you, it really helps to get started more quickly on this one. So thanks, and please let me know if this experiment you liked it or you didn't like it, and depending on that, I might do something next year. Okay, thank you.